the brains of this operation are Min Tang at Johns Hopkins University. So if you like anything, Min did it. And I will show you in particular what he spent 6 months in his office refusing to answer my emails doing that made this work. And of course, any mistakes are mine. So, spectral clustering. So some of you were at the first week back in July of the Theoretical Foundations for Statistical Network Analysis semester. And most everybody there was talking about, or half of the people there were talking about spectral clustering and using stochastic block models. So some of you know way more than you want to about that. Some of you, at least my neuroscientist, knows exactly what he wants to about that, which is presumably nothing. and hopefully you'll leave knowing nothing as well, so we won't have ruined you. But spectral clustering is a way to, you do care, of course, that's why you're here. Spectral clustering is a way to take the vertices of a graph and put them into groups. So looking for structure in the graph. And it's not the only way, it's the only way that I know that I know what it is that I'm talking about. So my one paragraph description of this part of my research program that I paste into all of my grant applications, for instance, goes something like, I want to find structure in a graph. I'm a statistician. I learned how to find structure in finite dimensional Euclidean data, endpoints in RD. I don't really know very much about how to look around in a graph other than hard ways, right? You can write things down and then figure out how to go about doing it. But if I could turn the graph into endpoints in RD, then I could use my, I like to say arsenal because I'm applying to DARPA. I like military words, so I can use my arsenal of statistical techniques to find the structure in the endpoints in RD. Each point is representing a vertex, and head on. Now the data processing lemma says that I will have lost something by doing that. I believe straightforward theorem says if I knew how to do it directly on the graph, I would do better, but I don't. So that's what I'm going to do. So spectral clustering then takes the graph and embeds it into RD and then composes clustering on that. Now, many people, again at that first week of the SNA, for instance, and in journal papers say spectral clustering is k-means composed with Laplacian spectral embedding. And I'm here to say, no, that's not true. It's some clustering algorithm composed with some spectral embedding. In particular, I will focus today on two particular embeddings, the Laplacian spectral embedding, take the Laplacian of the graph, the normalized Laplacian in this case, and do an eigendecomposition. And the adjacency spectral embedding, which is don't take the Laplacian of the adjacency matrix, just do a spectral decomposition of the adjacency directly. And then for clustering, k-means is what's standardly done. Standardly is probably not a word. K-means is what's done in the literature most of the time, but obviously what you really want to do is a Gaussian mixture model. If that wasn't obvious at 2 o'clock today, it will be obvious at 3 o'clock today. Okay, so we want to start with Bickel and Sarkar paper from the Annals of Statistics in 2015. They're investigating adjacency spectral embedding versus Laplacian spectral embedding for 2-block stochastic block models. And they looked at the within block variance. And they showed that for a large region of the parameter space, not for everything, but for the majority of the SDM parameter space, the Laplacian had a better limiting performance when considering within block versus between block variances. But that metric that they used, first of all, they could only do it for 2 block stochastic block models, but that metric is intrinsically tied to k-means. That is, within block, between block variances, is a k-mean sort of thing. And so it was right if you were doing k-means, but the question is what happens if you were doing any other clustering at the end. So I consider Gaussian mixture models composed with adjacency spectral embedding in a series of papers, I guess starting with a paper in JAZA in 2012. But the reason that I consider adjacency spectral embedding, I think I wrote a technical report coming on 10 years ago now that I handed to my wonderful, brilliant PhD student Daniel Sussman, who's now at Boston University, and told him, prove the conjectures in this technical report and you can graduate, and he did. But the reason that I wanted to consider adjacency spectral embedding instead of Laplacian spectral embedding was not because I thought it was a better thing to do, but rather it's easier, purely for mathematical expediency. I wanted to prove a central limit theorem for the Laplacian spectral embedding. I believed, and I was right, that first you do it for the adjacency. It's going to be easier. And then the Laplacian will be more difficult in degree, but not more difficult in kind. That is, it'll be essentially more tedious version of what we do for the adjacency, and since nobody had it for the Laplacian or the adjacency, I thought, let's try the simpler version first. My conjecture that it would be more difficult in degree but not kind, well, we can see whether or not we agree with that. Min doesn't agree, because he had to do it, but that's the deal. So then over the years, we proved this, Avanti Athrea and our colleagues proved the central limit theorem for the adjacency spectral embedding. So the corollary is that the top k eigenvectors for a k block stochastic block model are approximately a random sample from a mixture of k Gaussians in Rk. Okay? But they're not spherically symmetric Gaussians. And so it's not a k-means GMM, but a more general GMM. So if you used k-means after doing the adjacency spectral embedding, you would be losing performance. If you do the general Gaussian mixture model, you win. So today's talk is mostly based on Min's work, and this paper's just hit archive a month ago maybe. And it does the same thing for the Laplacian. It's a central limit theorem for the Laplacian, kind of mimicking what we did in the Sankhya paper. And furthermore, so Bickel and Sarkar did show that with their k-means subsequent inference, that neither Laplacian nor adjacency dominates the other. We're going to do k-means next. It's not the case that Laplacian is always the better thing to do, but sort of most of the time it might be, depending on what we mean by most of the time. Well, that's still the case when we do this, and furthermore, we can show conclusively that you shouldn't be doing k-means, you should do a more general Gaussian mixture model. And for this, we're going to use the okay, so let's do a few definitions and state some theorems. So the adjacency, the n by n adjacency matrix, the Laplacian, or the adjacency spectral embedding, x hat is just u root s truncated to d dimensions. Okay, so if I'm going to embed my n vertex graph into Rd, I just take the eigendecomposition of the adjacency matrix. So x hat equals ua sa root gives me the adjacency spectral embedding. This is easier than Laplacian, you'll see in a minute, but I mean, this isn't easier, but understanding it is easier. But I write x hat there. Okay, well, let's go here. So for the Laplacian, we're going to use the graph Laplacian, the normalized Laplacian, defined exactly like this for a general matrix M. We're going to consider the adjacency matrix as the matrix that we're taking the Laplacian of. For we just write it this way instead of I minus this for simplicity, because it doesn't matter for anything that we're doing. And just a quick note that we're not doing the combinatorial with Laplacian. So during that first week that some of you were here for, at one point somebody said, which Laplacian are you using? The speaker responded, there's only one Laplacian, and then the room split into two groups, one of which agreed there's only one Laplacian, and one that's, I think the ones who do stuff said, no, there's lots of Laplacians. I mean, for some mathematics, there might be only one Laplacian, and for practice, there's lots of Laplacians. So then, the Laplacian spectral embedding slide is a copy and paste of the adjacency spectral embedding slide, except now it's the matrix LA that I'm doing the eigen decomposition on, and so I have tildes everywhere, which is just the Laplacians have tildes and the adjacencies don't have tildes. And at the end, I get the n by d matrix X breve, which is exactly the same thing, the truncated eigen decomposition U root S of the Laplacian matrix. So we have X hat versus X breve, and we'd like to know which of those two to use. And I think I'm on recording, so I shouldn't say things that I normally say, but the argument for using the Laplacian until Bickel and Sarkar, or perhaps until this paper, kind of went something like this. The Fiedler vector is from the Laplacian. The Fiedler vector splits like min-cut. Min-cut's a good clustering. And so, let's just do the Laplacian whenever we want to cluster graphs, graph vertices. The last bit is a little bit standing on one leg, so if you're no longer trying to do min-cut, the whole story falls apart. On the other hand, if you don't know what to do, that's as good a thing as any. On the other hand, if you're trying to prove theorems, the adjacency matrix is better because it's simpler. Okay, so I want to talk about this random dot product graph. This is the latent position model with the inner product kernel. You're going to see that it's the right thing the right model to be considering for this kind of work. So I have a distribution F on RD such that on a subset of RD such that the inner product is always in 0, 1, so I can call them probabilities, treat them as probabilities. And a graph, and I'm saying X comma A, is a random dot product graph with distribution F. If the X1 through Xn are IIDF, those are the latent positions, they're unobserved, and then the adjacency matrix is just independent Bernoullis according to xi dot xj. So this gives me a generative model, a latent position model for graphs, a reasonably powerful one. We're going to consider the sparsity factor rho n, and so the x's, and we kind of want to keep this in mind for the next 45 minutes, the x's don't change as the graph gets bigger. I mean, we get more of them, but they're still IID F. F is fixed. But the sparsity factor hits the P matrix, so rho n times XX transpose is the matrix of the ijth element of that is the probability. So this rho n xi transpose xj is Pij. So it's the Pij that's shrinking if rho n is shrinking, or is yeah. So the stochastic block model that we like to talk about is a special case of this random dot product graph where the distribution F is just k point masses in RD. And that will then give you only k distinct rows of the P matrix, and we'll have our model there. And there it doesn't matter now if it's going to turn out. If for the purposes of considering stochastic block model mathematics, it doesn't matter that we're using a dot product kernel, because any non-trivial kernel will still give you the same thing, the same generative model, parameterized differently. So for adjacency spectral embedding, the we use x hat. The endpoints in RD are x hat, the estimates. And I call them x hats because they are explicitly estimates of the x's. As we will see in a moment, the x hats, the x's here, if we conditioned on the capital X, we'd have n times d parameters. They'd actually be the parameters of this random graph model. And the x hats consistently estimate those parameters. They're formally statistical estimates of the x's. So I talk about them. The x breves for the Laplacian spectral embedding we'll see are not quite that. They're not trying to be quite that. Okay, so the law of large numbers for the adjacency spectral embedding says, okay, I'm going to also play fast and loose verbally with this a lot. That you can see that the random dot product graph or latent position model with dot products is not identifiable in the sense that if F is hit with an orthogonal transformation, I get the exact same model. So I always have these orthogonal matrices W, or if I don't, I'm supposed to. These orthogonal matrices W. So x hat. So think for a moment that rho were the constant 1. So I have no sparsity interest here. Then the x hats are looking like x, is what this first line says, but only if I hit them with the right orthogonal matrix. So if I were trying to actually estimate the parameters x, I would have to know this unknowable orthogonal matrix. If I'm just trying to cluster, then it doesn't matter. So for subsequent inference, I don't have to know the unknowable thing. For mathematics, I have to know that there exists an unknowable thing, which is part of the work. Okay, so x hat looks like x, or like root rho x if my sparsity factor rho is less than 1, then the P matrix is what I'm decomposing, or the A matrix is drawn P. And so the P matrix is what's governing my decomposition, and so the x hats will look like root rho x, which is what they should look like. Okay. So the law of large numbers theorem, sort of here at the bottom, is that if rho goes to 0, but no faster than that, then I get a convergence of x hat to rho x, root rho x. It goes to this constant right here. And the constant's entirely in terms of the distribution capital F. Okay, so there's my law of large numbers.
Sorry, so I'm just trying to understand. So the right-hand side of the bottom result means, this constant, what is that? Because I'm looking at the top, and I guess I'm trying to understand, like, what is the term that's left over? In other words, why I would expect that you would have a remainder term that's going to 0, which I guess you kind of do have in some matrix norm.
Right, but here, so the deal is, though, that as n goes to infinity, these matrices get bigger and bigger, more and more stuff in them. So that's sort of part of the idea of all of these limit theorems, is that it doesn't go, you don't need it to go to 0. You just need it to go,
The normalized error goes like 1 over.
Exactly, precisely. So it doesn't actually go to 0, which is sort of the first conceptual thing to get in your head. You don't want your law, I am looking like this, but looks like doesn't quite mean what you think. Right. But as you know, there's only n times d things that I'm estimating. And these matrices are n by n. And so that's why you wouldn't have to have that going to 0 in order to get what you want.
And how do you estimate, that is independent of d, d is fixed.
Right.
But it will depend, I guess. Because
right.
You're truncating, you're essentially projecting on a d-dimensional space.
Right, and there's a d there's an implicit d in all of these things, that's right.
Yes.
But
how do you select that?
Good, I was going to say.
Because I read your paper, I found before I found it's an archive on Wednesday night.
Yeah, so
Julia
hinted at but in fact explicitly asked a really great question for any practical purposes. This paper doesn't care about that.
Exactly.
I care desperately about it, but the talk I gave last month is all about selecting the dimension. And of course, we know that there's no, model selection is an impossible problem. So you do your best. There's a lot of literally exploratory data analysis and scientific interest in things like that. And it really does matter. Now, in theory, it's easy to do in practice. That is, universal singular value thresholding works. The one thing I know for sure in practice is you don't want to use that because it doesn't work in practice. And so essentially you always look for the elbow in the scree plot, whatever that means. So I can talk at enormous length about choosing D, but here we're assuming D is known.
Okay, can I ask one more?
Actually, yeah, let me say one more. Yeah, let's let you go first.
Okay, so because actually you are doing projection on a D-dimensional space, yes? This D, yes, depends on your sparsity, because when n goes to infinity, the way how you select D is linked to your rho n, to your sparsity parameter, intrinsically. I mean, right now you just fix D, but in fact,
Well, the true D is fixed here.
through this fixed, yes. But you have a sparsity parameter. Sometimes you say, okay, rho n is 1,
Right,
and
but-
your paper also you have, yes,
Right.
exactly. So now, what if you take D, okay, so you have all your eigenvalues, they are non-negative, definitely. So can you just select D as just number of non-zero eigenvalues?
No, that is what I know. Because
No, not practically, but I mean, not in theory. And then allow D to change with n. So that you will control your...
right, but the adjacency matrix is not ranked D. So there's n non-zero.
But for Laplacian.
But you will have, well, even for the adjacency matrix though, in some sense, if the kernel is finite dimensional, which it kind of is in our case, I mean, eventually
There'll be
you
no.
should see concentration of the eigenvalues of A, which should allow you to.
That's right.
So I think what Julia is suggesting is like, is there an analysis that lets you have a D hat as a function of n that comes from thresholding? You want the
That's right.
threshold.
Yeah, then that's exactly what they are. That's exactly what they
Yeah,
are.
that's it.
And
The
in
analysis
practice,
doesn't do that, but your analysis
No.
doesn't do that, right?
Yeah,
No.
you just don't do it, but I mean, you can potentially,
That's
because
right.
that's linked to rho n.
that's right. The method we use in practice, I like to use the profile. So you do a profile likelihood analysis of this and that as a function of n is guaranteed. You can prove that it will converge to the true D in the limit, but no, you can do that. But whether it's a good D for the n that you have,
No, that's
Is
a
another-
different
yeah,
story.
that's
That's
a-
it.
right.
We're talking about just asymptotic.
right, to get the limit result, you can do that. Now, at the very end, which might be pretty soon, I will point out that all of this mathematics, it turns out that if there's a true D, and the D that we embed into is smaller than the true D, the mathematics pretty much goes through. If the D that we embed into is larger than the true D, no one knows how to do the mathematics. And Tao and Vu said they don't know how to do the mathematics. So if we embed into too many dimensions, one of the main open problems is what happens when you embed into too many dimensions, and we don't know the answer to that. If you embed into too few, you have bias, of course, and you've truncated too much, but everything is still working like it ought to. But the K plus first eigenvector of a K block stochastic block model is a mystery to us.
Because, okay, it's just a last comment. So, because I do think that this is your projection is actually on the D-dimensional space. It's actually linked to what Peter Bickel did in terms of, and Binu did in terms of regularization.
Yes,
And yes, that's
that is true. And the regularization is another,
exactly another way of doing the same.
Right.
Story.
but we can't do a CLT yet for the
I
regularized.
know.
Yeah,
I know.
that's right. But I agree, that's right.
After that, I'll stop.
In practice, the regularized is the way to go, says me.
Not necessarily. That's arguable. But I will stop.
It's arguable, but says me. If I have to do Ben's data, I'm gonna regularize.
No, don't do it because it will take forever. But we
It
can do
doesn't take
afterwards.
any time at all. Okay, so that's the law of large numbers. Now I want a central limit theorem, and so I'm going to talk about the x hat I being the ith row of this adjacency spectral embedding. And what I get is that some arbitrary, or no, not arbitrary, some unknowable orthogonal matrix W times the x hat I looks just like xi in the sense that it converges that root n to a Gaussian. Not only that, but we know that in this case, I'm not conditioning on the xi's, so it's a mixture of Gaussians where I integrate against df, the distribution from which the x's are drawn, but I know the covariance matrix, the limiting covariance matrix for this, again, in terms of the distribution f that I have. So we get convergence to a mixture of multivariate normals. And the same thing happens if rho goes to 0, but not too fast. And the not too fast here, we just use Liu and Peng's results from 2013 or whatever it is. They can make their stuff work for log 4, and so our stuff works for log 4. And so the x hats are limiting normal around root rho xi. So for the purposes of saying what happens when I do k-means after I've embedded, or versus a general Gaussian mixture model, if I know these limiting Gaussians and their covariances, I can write down how well I will do if I use spherically symmetric Gaussians to cluster versus general Gaussians.
Is there anything that's particularly specific to Bernoulli variables here? I mean, I can understand that the moments are controlled very strongly or whatever, but is there any reason this result doesn't, really feels more like a result about symmetric random matrices generated according to some model or something, or am I misunderstanding?
No, you can generalize it to a more general setting. There are some specifics associated with the Bernoullis, or, finite multigraphs, let's say. So you have
But I mean, if you had Poisson instead of Bernoulli, I think it would be fine.
a little bit trickier
It's
because
trickier.
if you don't, instead of Poissons, if you have multinomials where it doesn't go arbitrarily large.
But I
You
mean, the
need to have
tails
some
should be
conditions for
fine.
the.
You just don't, I mean.
But
let
we
the
can do-
means go.
We can do some of that.
Right.
No, but you're right. I'm talking about the simple graph here, but we can generalize it quite a bit, but not as far as we might want to.
But then also, like, is the CLT surprising, or is this like an instance of a broader class of problems for which such styles of CLT are known? I mean, either from the point of view of proof techniques or just the way the result.
It's not a corollary to something that was in the literature. I don't think it's surprising. I don't think it's particularly surprising, but the random matrix people, I mean, when they visit me in Baltimore, when they visit you, you probably get the same thing. They tell me the answer, but I can't for the life of me figure out that they've told me the
It's
answer.
also the same theories, like if you, for example, have equivariance matrix, yes? Then you need to have certain conditions. For example, your all eigenvalues should be
You just have to
strict.
control the.
Exactly. So one of them is all eigenvalues should be distinct. And I think that you have somewhere about, previous paper where you have all eigenvalues distinct. I don't remember whether you actually relaxed it here.
Right, we relax, so we don't require distinct eigenvalues.
Yeah, but
Right.
anyway, so when you have this,
Yeah.
then you can show for a general covariance matrices that, eigenvalues are, normal distributions, but the result for eigenvectors
Right.
is way, way
Right.
more involved, but it holds. Here, because you're gonna have symmetry and you actually have this factorization, you kind of,
Right,
so it's not
it's a bit
surprising
easier.
result, but I mean, it's
Yeah.
involved results, it's
Right.
tedious.
Right, but eigenvalues are easier.
Oh, yeah, nobody argues, yeah, I mean, eigenvalues is much, much easier.
I could probably do those myself. I could not do this without min. So the stochastic block model, this finite mixture of k point masses. So the corollary then, if we're doing SVMs, which I want to do at the end, is that conditioned on xi being from one of those point masses, I actually get that Gaussian with that known covariance matrix. And so I know my mixture of Gaussians, my limiting mixture of Gaussians for the stochastic block model. Now, this paper reviews that and then essentially does the same thing for the Laplacian. And so these are kind of the same. X tilde is my Laplacian spectral embedding. Well, that doesn't look like X, or it doesn't look like rho X. It looks like root rho times t to the minus a half of X, where t is the, as it says, the diagonal matrix with expected vertex degrees. So it's kind of what you'd expect. So that's what X tilde is estimating. So X Priebe looks like X tilde. X tilde is, you can get it from the X's and the rho, but you can't, but it's not an estimate of the X's quite the same way. So the law of large numbers, again, we define some things that only depend on the distribution capital F, and the law of large numbers says that n times the squared Frobenius norm of X Priebe minus X tilde goes again to a constant, a different constant. C
That was
tilde.
going to be my next question. I mean, the scaling, it feels like the combinatorial Laplacian would have been the more natural scaling to pick up. Is there, I mean, if you wanted the same scaling of the spectrum as in the adjacency
Right.
matrix, then,
Right.
so why did you change your scale? I mean, I'm just curious to know why you would change the scale.
Because I wouldn't use the combinatorial Laplacian for the actual application like I would use the normalized Laplacian. Spectral, you could say spectral clustering is clustering followed by that, but I don't think even you
Yeah,
would,
yeah,
right?
yeah.
So that's the answer.
I just curious. Yeah.
To some extent, practicality seeps in there maybe.
I was more trying to understand, I mean, oftentimes people study the normalized Laplacian because it has the nice property of bounded eigenvalues
Right.
and everything, but I was just trying to understand if there's anything there, but I think it's just, you're just choosing an implicit choice of scale, right? I
Right,
don't think
that's
it's
right.
more of
And trying to figure out what that scale does and whether it does, you know, how it behaves in terms of subsequent inference, which is the goal. So when I have this version of sparsity, it turns out that it's n times rho times the squared Frobenius norm that goes to the constant. Okay, so instead of what we had in the
Sure.
adjacency, but what you'd expect. So now if we look at the CLT version of this, the ith row of the Laplacian spectral embedding, X Priebe sub I, looking like X tilde sub I. Well, we want to note that X tilde sub I is Xi over this root, this sum. Okay, so that's what we'd expect, so we'll keep that in mind. And we see that the CLT here is that n times X Priebe looks like X tilde sub I. And so we still get asymptotic normality. Here's the sparse case, so it's n times root rho that you have to hit this with because, well, the X tildes are shrinking. The thing I'm aiming at is shrinking beyond as n goes to infinity, forgetting about the rho, and so I have to blow it up by more in order to get my CLT. So it is, in sort of partial response to Patrick's comment earlier, it is what you'd expect it to be. Although this isn't necessarily what I expected. I don't think we had any idea what the covariances were, and those are the key for subsequent inference.
Yeah, that's probably understandable, I think, for some, anyway, we can talk about it later.
Good. I hope so. And then for the stochastic block model, we get the same thing. We get n times root rho is trying to hit the point mass where the point mass shrinks, according to that. And that's a sum over n things. So I got a root n in the denominator there. Okay, so if that's understandable, the place I'm going to start is here. This helps. So let's look at Erdős-Rényi, and this is Erdős-Rényi p squared. You can ask Min why it's not Erdős-Rényi p. I mean, you can see why. But if you have an Erdős-Rényi with probability p squared, that's a latent position model where everybody has latent position p. And so the adjacency spectral embedding is exactly that. Root n times the x hat is Gaussian around P. So that's nice and beautiful. The Laplacian, it's n times x breve that's Gaussian around 1 over root n. Okay, so that's fine. I'm blowing it up by n, and so it's still a perfectly fine limit theorem. And now, as Patrick is saying, everything kind of makes sense. So the thing the Laplacian is aiming at is shrinking. I blow it up by more, but in both of these cases, I get a Gaussian with some covariance matrix that Patrick says I will really understand quite well. Well, for the Erdős-Rényi, the key is those covariance matrices are different. One's not better than the other. They're just different. That's in some sense, at the Erdős-Rényi level, this is the difference between Laplacian and adjacency. If we did combinatorial, there would be no difference at this slide. Okay, a slightly more interesting example is a two-block stochastic block model with that B matrix, that connection probability matrix given up there. So we're getting close to what you care about, Ben. I mean, this is essentially where I get the result you have. So this is, again, D equals 1. It's a one-dimensional stochastic block model where you have some vertices, latent positions drawn at P and some drawn at Q. We still get our limiting Gaussian, but at this point I asked Patrick, okay, so write down the intuitive understanding, and I don't know how to do it yet. I'll show you what I can do, but this isn't it. So I mean, you can write this down. If you give me any B, I could write this down. This is still univariate. So trying to understand one-dimensional SBMs with more and more blocks is one way to go about it. You'll always be univariate, and you can get the idea for how the variance goes. Then when you go to two-dimensional SBMs, even the two-block two-dimensional SBM, it gets a little bit more involved. But conditional on it being from P, I get this Gaussian and this Gaussian. So for the adjacency spectral embedding, I literally get a Gaussian around each of those. And for the Laplacian embedding, I literally get a Gaussian around, well, points that are shrinking toward the origin. But the shrinking toward the origin versus the blowing up stabilizes, so they're still competitive with one another. The idea that for subsequent clustering, neither would dominate the other is sort of intuitive at this point. There's no reason to think that this covariance matrix is always smaller than that one or vice versa. In fact, it's not the case. Okay, so for just a couple of minutes, I want to sketch one, maybe the key and fun part of the proof. This is the what Min did. Sounds easier than it was, I believe. So the Laplacian spectral embedding is x breve. Davis-Gahan tells me that the two eigenspaces are close. So Min's proposition B2 in the paper is that there exists an orthogonal matrix such that U tilde P, that is the Laplacian applied to the P matrix, times U tilde A, that is the Laplacian applied to the observed matrix, is essentially this orthogonal matrix. So you could do that really nicely if I had a P and a P or an A and an A, but now I want to talk about P and A, etc. And then his main result is this fact that the orthogonal matrix that satisfies the Davis-Gahan sort of leads us to, allows us to swap. So all I wanted to do was move W star through the S root, or the S minus root in this case. So I have it on this side, I want to move it over here. That took him a long time. And then I also want to be able to switch A and P. Okay? And we can do that. So it turns out that that particular W star has this important property. So let's talk about that in a little bit more detail. So Davis-Gahan gives us not only UA transpose looks like UP transpose. I'm forgetting about the tildes here, but this is all for the Laplacian. But it also has this first display equation there. So this is sort of the key. So let's consider these two terms. So on the right-hand side of that display equation, I've got a UP transpose UA times S inverse A. And over here, I've got a S inverse P and a UP UA. So if I could combine those, the right-hand side would be not only more pleasant, but actually amenable to manipulation, if I can use multi-syllabic words in at one time. So first of all, since they both have orthonormal columns, I can say that UA transpose looks like UP transpose, and that there is a W star that looks like UA transpose. So that's relatively straightforward. But the idea that W star satisfies this important property allows me to, in the red up here, well, first of all, I'm allowed to replace UP transpose UA with W star, and I'm allowed to bring it through the SA or the SP. And so I'm going to take that display equation up there, use Min's lemma B3, and I'll get this final result right here. And this is the key result, because this is X Priebe. This is the Laplacian spectral embedding, and this is X tilde, or X tilde, the thing the Laplacian is aiming at. X tilde might have to be hit by another orthogonal matrix, unknowable orthogonal matrix, but that's okay. So X Priebe looks like X tilde, and because of the manipulation we've done, the looks like is actually pretty simple. It's just the difference between the Laplacian on the adjacency matrix and the Laplacian on the true P matrix, the true unknown P matrix that we can get a handle on, plus something else that we get a handle. So this trick of being able to fiddle with the red up there in terms of this has made the right-hand side here amenable to essentially brute force manipulation in order to get the law of large numbers, the constant that we're going to. And so to the extent that I was right, and then everything else is just ickier, but the same idea as the adjacency spectral embedding. So to the extent that this is an important and new thing, I was wrong. To the extent that Min went to his office and 6 months later came back with it, from my perspective, I was right. But this is in some sense the key to the turning the adjacency spectral embedding crank into a Laplacian spectral embedding crank. Okay, so so now I have mixtures of Gaussians for stochastic block models in both cases. So we want to use Chernoff information. So let's first talk about a little picture. There's a two-block stochastic block model. If I do a Laplacian spectral embedding on that one instance, here's what I get when I have n as 1,000. The two Gaussians, those are the empirical level curves for the Gaussians that I've got there. When n is 2,000s, they're more and more separated. Everybody knows that as n goes to infinity, not everybody. Some people know that as n goes to infinity, they separate enough that you can do perfect clustering. But when n is fixed and finite but large, what do we have? Well, among other things, we have non-spherically symmetric Gaussians. And so k-means may or may not be a good idea. So here's a plot. So let's talk about n equals 2,000, corresponding to the right plot here. So at n equals 2,000, the y-axis is log 10 of the clustering, of the misclustering probability. So the top curve at n equals 2,000 is green maybe. That's how we do with k-means, 10,000 Monte Carlos or something on this. And you get an error of about 10% if you do k-means. If you do the third curve, the red curve at 2,000, is an error of about 2% if you do general Gaussian mixture models. I mean, it's a huge difference, the difference between getting fired and getting a promotion, perhaps, in practice, to not do k-means. This is for Laplacian spectral embedding. You can't make the difference between tenure and not tenure, because who cares, right? It's just a journal paper. But if you're gonna have a real job, you could get fired or not. The purple curve that underneath the green curve is the oracle k-means. So if we knew the true Gaussians from theory, and then backed off to an n equals 2,000 large sample approximation, that's how good you do with k-means. And then the psi n curve is the same thing for the general Gaussians. So don't do k-means, do a general mixture of Gaussians. Now, real quickly, the bias variance trade-off tells us that if we're in d dimensions, we're estimating more parameters, and so it could actually be a good idea to use k-means if n is small. But that's another story.
Yes, the thing is that, you know, the way how much Gaussian you look like depends on your sparsity. It will.
Well, if what you're saying, I'm gonna agree with you and make it so that you said how large n has to be before it looks like a Gaussian depends on your sparsity.
So the point is, instead of, so what we found empirically, so for example, if you do LC, so Laplacian embedding, without regularization, okay, you have some mess. Then suppose when you apply regularization based on this decay test, that's what Beam did, okay? And then you start getting much better. You see really exactly the stuff that you're showing, yes? But that's after regularization. So the idea is that instead of doing this Davis-Kahan bound, which it takes enormous amount of time to find optimal parameters for regularizing, you can actually put your loss function as making it normal.
Yep.
So you try the best regularizer. So essentially it's like finding your W matrix.
And if you
then do this.
if you read the conclusions of the paper, and I think you did, we say that if you could do this central limit theorem for the tau regularized Laplacian, you could develop a theory for optimal regularization, which is one of the main goals, I guess.
But I guess you can go the other way around. You can say that since there should exist W, such that X W is, you know, multivariate, follows multivariate norm. So let's try to find the regularizer. Let's essentially try to find such W that given such finite sample, you look as mixture of Gaussians as possible. So instead of doing Davis-Kahan bound.
I'm up for it. I'm okay with that. Okay, so I'm skipping section 4.1 of the paper, but that's going back to Bickel and Sarkar, and they're within block variances being insufficient. But the key is that what they did captures only the trace of the block conditional covariance matrices, and so that's like the oracle k-mean. So all they're telling us about is which ASE versus LSE is better from the point of view of that purple curve, which is not the best you can do if you accepted a more general clustering. Okay, so what we want to do in this next little bit is talk about that oracle Bayes lower bound, the GMM lower bound. And so we want to ask which embedding is better without talking about what clustering procedure I'm going to be using. That is, I want to know what's the error rate of the best error rate over all possible subsequent inference procedures for LSE versus over all possible subsequent inference procedures for ASE. And here we can use the CLTs for the stochastic block model to give us this. So here's a little bit of development of pattern recognition and Chernoff information that I'm not going to go through in detail because of time. But the Chernoff's information is intrinsically linked to this to the Bayes error. So if we define for two distributions F0 and F1, if we define the Chernoff information this way, and we have the inf over t inside of the log here, if we follow Chernoff's definition and use that, then we get that the limit as the number of samples, m here is the number of samples, goes to infinity of 1 over m times the inf of this thing that looks like the Bayes error, is exactly minus the Chernoff information. And so in fact, the Chernoff information between two distributions is the exponential rate at which the Bayes error decreases as the sample size goes to infinity. So if we take into account the Chernoff information of the multivariate Gaussians given by LSE for a stochastic block model, and the multivariate Gaussians given by ASE for that same stochastic block model, we can look at the ratio of those Chernoff informations and ask which one, in a limiting sense, in a large sample sense, is superior for subsequent inference, assuming you do the right subsequent inference, the Bayes optimal subsequent inference. Now skip that. This says that I can do it for block models more than 2. So generalize it to K block models. The inf over all decision rules, so the Bayes error, is minus the minimum, the pairwise minimum of the Chernoff information. The Chernoff information. Okay? So this right-hand side is what we will use to compare ASE and LSE. And since they're multivariate Gaussians, we only care about C for 2 Gaussians with covariance matrix sigma naught and sigma 1 and means mu naught and mu 1. The point here is because x breve and x hat are aiming at different things, we have to take a lot of these things into account. The reason we use Chernoff information is because it takes them into account for us relatively nicely. We could kind of use any F divergence. This one is expedient. Okay, so let's do that. Here's the stochastic block model, positive semi-definite B matrix. When ASUE is used, there's the Chernoff information, rho sub A. And I can calculate that if I know the B matrix because I know the mu's and the, or the nus in this case, and the sigmas. And similarly, here it is for the Laplacian. It's a different expression in terms of different parameters, sigma tilde and nu tilde. The things we're aiming at, the multivariate Gaussians are different, but the expression itself, other than that, is the same. And now note that the larger the Chernoff information, the better the performance, and so the ratio rho A over rho L, if that's bigger than 1, then that says ASE is superior for that block model versus less than 1. So here's our stochastic block model from before, our 2-block model in R1, and extraordinarily easy to just write down what these Chernoff information, if that's the plural of information, what these Chernoff informations are and look at the ratio, and we can say for whatever choices of P and Q and pi, does one dominate the other? And if we do this, you get kind of what you get in Bickel and Sarkar, but they were using only sort of spherical symmetric Gaussians, the k-means approach. So it is fundamentally different. You can find cases where their rule would have given you the wrong better of the two, but other than that, it's just a better way of looking at it, perhaps. Let's skip that. We also can go to more than 2-block models. So here's a nice block model to look at. It's got the B matrix has P's on the diagonal and Q's off diagonal. So if P minus Q is small, I think I use Q minus P. If P minus Q is small, this problem is hard. The clustering problem is hard. And we can just make a plot of the ratio rho A over rho L, and here's the 1 point. So sometimes LSE is better and sometimes ASE is better. But more to the point, any point in here represents a B matrix. So for any point in here, I can find the ratio, and I can go on and just do a Monte Carlo for some value of n. Depending on rho, as Julia says, n might have to be large before the large sample theory has kicked in. But for instance, here's 2 points on that figure. That's what it is. 2 points on that figure. the first one, the ratio is greater than 1. And if I do 1,000 Monte Carlos and look at the performance, turns out that ASE gives you perfect performance, and LSE is very bad. Whereas for this other one, where the ratio is less than 1, ASE is very bad, and LSE gives you perfect performance. So the idea here that one or the other is what you should hitch your wagon to is clearly not the case. Both of these have to be in your quiver. If that's wagons, people with wagons have quivers. Okay, so neither is better. It depends on what you're looking for. Now, that's great. I can make this plot. You tell me B. I can tell you the ratio. You can do Monte Carlos to verify if I can make n large enough, right? To show that, yep, bingo, we do really good with one and not really good with the other. But what I really care about is this two truths idea. So at the a couple of times during that first week, people were talking about clustering, and then a few of us, Peter Bickel and me, and maybe it was Sophia or Patrick or somebody, kept saying that clustering is whatever clustering is. Like, right, what's the right answer? Whatever you find. Okay, so for a stochastic block model, there's a clear clustering. I mean, clear what the clusters should be. For Ben's data, there's, depending on how you look at it, this is a true cluster or this is a true cluster. So in our JAZA 2012 paper, this is really what I care about. And I don't know how to do it, but I'm hoping that the theory that we've gone through in the last hour will lead to a resolution to the following sticky wicket. So in the JAZA 2012 paper, we had a real data set in there. Do something on real data, theory, simulations, and then something on real data. Well, the real data happened to have 5 classes. It wasn't a stochastic block model, it was real data, it had 5 classes. And in the example in that paper, we showed that if you do ASE and then cluster, you get one of the classes and then is clearly separated, and the other 4 are mixed together. And if you do LSE, you get one of the classes separated and the other 4 are mixed together. And the class that's separated for the 2 is a different class. So ASE pulls 1 out of the 5, LSE pulls a different out of the 5. There's 2 right answers for find me one cluster in here, and they both found it. Found one of those 2 right answers. Another point is diffusion tensor MRI, and this one I think is going to give us a hint as to how to go about this. So I've got this giant brain, it turns it into a graph view via diffusion tensor MRI, which I don't know what it is, but I know I have some papers. Does a bunch of weird stuff. But if we think of the brain as having 4 classes of voxel, of neuron, they're either in the right hemisphere or the left hemisphere. They're either white matter or gray matter. Well, going back to the Fiedler vector, motivation of the Laplacian, the right hemisphere and the left hemisphere should be less connected than anything else. And so the min cut is kind of a long hemisphere. If I do Laplacian and then cluster the voxels, I get right hemisphere, left hemisphere. Got a bunch of data here. It works for an entire set of 42. All 42 of them find left and right. If I do adjacency, it finds white matter versus gray matter. Not wrong, not right, just different. Okay? And so the idea of what the 2 representations are pulling out is what we really need to know, because if I'm going to take Ben's connectome and I'm going to look for structure in it, well, I can pick one of the 2 embeddings and look for structure in that representation. But there are many different representations, 2 that we've discussed here today, that will find different kinds of structure. And we can do that empirically. I'm hoping that the theory Min's paper here will lead to a follow-on that allows us to understand which of the 2 embeddings to use if you have a prior that you're looking for some particular kind of structure. I don't have that yet, but if I did, I would use it tonight on Ben's data. Okay, so the conclusions are that I talked for an hour and it was fun. And that Yulia has work to do in order to explain to me her follow-ups. Thank you very much. Have a pleasant day.
Questions from Carey? We already had some discussion and interruption in the middle. Yes?
Do you have any questions, Yulia, or
Yes.
comments?
Yeah, so what about if you can, I guess the idea with information criteria could be also extended to find the optimal number of clusters.
Yes, that's kind of like the same thing. That's maybe a simpler version of this more general thing that I'm going to do. That's right. So if you have a stochastic block model, then they should all have the same number of clusters. But if you had a more complicated graph, or even a stochastic block model with a lot of blocks, given how large your sample, your vertex set is, then the best number of clusters. So we're trying to figure that out, and we cannot do it. And in fact, I told Min to send me something by Thursday morning so I could use it, and he didn't. So it must be hard.
Because I guess that the whole idea now you operate within the multivariate context, so you can actually, you can just use the information and stuff, yeah? And
Yep.
so you get something like a BIC essentially.
Exactly. It's
Pretty
perhaps
much.
a
Or
better
BIC.
BIC.
Better BIC.
That's
or
what I'm
BIC,
thinking.
exactly.
That's
So
it.
some information criteria solely on,
The pre-information
but-
criteria, if it's good.
Otherwise
the shelf.
Of course, there is no question about that.
But-
But it's not only, but it's also parameters, like, you can put a number of parameters within this information criteria, not only number of clusters, but if you're trying to estimate, for example, P and Q.
Right, but you could also put how much, so the k-means is just a special GMM. You could also go back to sort of Levina and Bickel and talk about, well, what do I do if I have a easier estimated
Region of, yes, that's right.
covariance matrix, have it,
That's
be
right.
diagonal or something. Go all the way back to
Yes, that's right.
Raftery's MCLUST and all the different possible models, but do it with this
Of
information
course,
criteria
that's
instead.
exactly what we're gonna do tonight.
The problem, one of the problems is this one. So if it's not a finite rank model, then the actual rank grows as n grows. And so now I should be okay because I'm always embedding into smaller dimension, and that math is a little bit easier. But the embedding dimension, now we're back to where you're saying that where you want to embed actually grows as n goes to
Yes,
infinity.
but it should
Not
just
just
grow
your
much slower.
right, and it
That
grows
will
much
be
slower.
enough, then that will be enough to get the same, If you
Right.
do the same, the usual stuff like with, lower n over n, whatever. Like with usual covariance, that when you have like a bending or threshold and whatever, the same conditions, under the same conditions should prove it.
I hope so. Very good. Have a pleasant day. You should release your convicts.
Indeed, let
Thank you.
everyone go to think deeply about what Carey's told us.
So Ben, Yulia might be able to help us. However, in the past, she keeps saying things that she thinks I understand and I don't understand. So
No, it's
we're
because
gonna-
Carey's trying to escape me. We have a long story.
we do have a lot of
Let's
story.
give Carey the applause then.
Thank you, Sophia.
Hobby